When we flip a switch, the light turns on instantly. But what if I tell you that the electrons inside the wire move slower than a snail? The average speed of electrons in a wire is just 0.2 millimeters per second. So how does the bulb glow the very moment we switch it on? Another interesting fact. We commonly say that the flow of electrons is current, but in an actual wire, current flows in the opposite direction of electron flow. Have you ever wondered why? And here is another common doubt. A transformer can increase the voltage of electricity. If the voltage goes up, shouldn't the energy and power also increase? Electricity has been a part of our daily life for many decades, but most of us still do not understand some very important things about it. In this video, we are going to learn 7 things you must know about electricity. Hi friends, welcome to a new video from Science Simplified for All. If you have not subscribed to this channel yet, please do that and tap the bell icon so you will be notified as soon as new videos are uploaded. Let us begin with a very basic question. What exactly is electricity? According to the textbook definition, electricity is the flow of charges. There are 2 types of electric charge, positive and negative. If we look at an atom, the proton carries a positive charge and the electron carries a negative charge. Protons are locked inside the nucleus, so they do not normally move anywhere. But electrons are comparatively free to move. Because of this, electrons are the ones that usually flow in a conductor. That does not mean positive charges never move. If an atom loses 1 or 2 electrons, it becomes a positive ion, and such ions can move from place to place. But in most common situations, when we talk about electricity, we are talking about the flow of electrons. For example, in this picture, a bulb is connected to a battery. Electrons flow from the negative terminal of the battery through the bulb and finally reach the positive terminal. This flow of electrons is what we normally call electricity or electric current. In the battery and bulb example we just saw, there is a small twist. Electrons actually flow from the negative terminal of the battery towards the positive terminal. But in every textbook and every diagram, we say that current flows from positive to negative. This is where many people get confused. The real reason is very simple and a little historical. Centuries before the discovery of electrons or protons, scientists had already observed the phenomenon of charge through what we now call static electricity. You may have seen this yourself. When you rub a plastic scale on dry hair, it can attract small bits of paper. That is static electricity. Long ago, scientists also noticed that when a glass rod was rubbed with silk, it could attract certain materials. And when amber was rubbed with fur, it showed similar attraction. They called this property charge. From repeated experiments, they realized that the charge on glass and the charge on amber was opposite in nature. It was Benjamin Franklin in the 18th century who decided to name the charge on glass as positive and the charge on amber as negative. It was just a naming choice. There was no deeper reason. Much later, scientists discovered that this effect was actually due to the transfer of electrons. When fur was rubbed on amber, electrons moved from the fur to the amber, giving the amber the charge. Since Franklin had already called amber's charge negative, the newly discovered electron was also assigned a negative charge. That is where the confusion began. For the mathematics to work correctly, the direction of the flow of positive charge has to be taken as the direction of current. But the actual thing flowing is negatively charged electrons. That is how we ended up choosing the current direction opposite to the direction of electron flow. If Franklin had chosen the opposite names back then, today, the electron flow and current direction would have been the same. But because of that old convention, we still use the reverse definition. For the rest of this video, do not worry about the direction of current versus electrons. Thinking about both together will only create more confusion. So, we will leave this topic here and move forward. Now let us look at 3 important concepts in electricity: voltage, current, and resistance. To understand them easily, the most common and simplest example is that of water flowing through a pipe. Imagine 2 tanks filled with water, both at the same height and connected by a pipe. Even though the pipe is full of water, nothing flows through it because the water level in both tanks is the same. Now imagine one tank is placed at a higher level than the other. Water immediately starts flowing from the higher tank to the lower one. Here, the force that pushes the water through the pipe is the pressure created by the height difference between the tanks. In electricity, voltage is similar to this pressure. It is the voltage that pushes electrons through a conductor, allowing current to flow. We measure it in volts. When we talk about the amount of water flowing through the pipe, we express it as 5 liters per second or 10 liters per second. In electricity, this is equivalent to current, the amount of electric charge flowing through a conductor per second. It is measured in amperes. The flow of water depends not only on the pressure difference, but also on the resistance of the pipe. If the pipe is rusty inside, the flow of water will face resistance. If it is smooth, water will flow more easily. A thicker pipe allows more water to flow, while a longer pipe reduces the flow. So, the length, width, and smoothness of the pipe all affect how easily water can flow through it. Similarly, in a conductor, voltage causes electrons to move, but how much current flows depends on the conductor's electrical resistance. Conductors are materials that allow electrons to move easily. Metals are good conductors because in their atoms, the outer electrons are loosely attached. So, in a metal wire, there are many free electrons available to carry current. But when electrons move through the conductor, they collide with the atoms inside. This slows them down. Just like rust inside a pipe slows water, this opposition to flow is called resistivity, a property of the material. Copper and silver have low resistivity, so current flows easily. Tungsten has high resistivity, so current flow is harder. In addition to resistivity, 2 other factors affect the resistance of a conductor: its length and thickness. A longer conductor offers more resistance, while a thicker one offers less. So, after considering the material, length, and thickness, the total opposition to the flow of current through a conductor is called its electrical resistance. In the case of water, pressure and the resistance of the pipe control the flow. Higher pressure means more water flow. Lower pressure means less flow. And when the pressure stays the same, if the pipe becomes longer or thinner, the water flow reduces. If the pipe becomes wider and smoother, the flow increases. So the flow of water is decided by 2 things: pressure and resistance of the pipe. Exactly the same happens in electricity. The amount of current flowing through a conductor depends on 2 things: the voltage applied across it and its resistance. If the voltage increases, the current increases. If the voltage decreases, the current decreases. If the voltage remains the same but the resistance increases, the current decreases. And if the resistance decreases, current increases. This relationship between voltage, current, and resistance is expressed by a simple rule we all studied in school: Ohm's law. Current equals voltage divided by resistance, or I equals V divided by R. It is also written as V equals I times R. Earlier, we saw that when electrons move through a conductor, they collide with the atoms inside it. During each collision, a small part of the electron's energy is transferred to the atoms. As a result, the conductor becomes hot. This heating effect is called Joule heating. The amount of heat produced depends mainly on 2 things: the resistance of the conductor and the amount of current flowing through it. In fact, there is a direct formula for this. Heat produced equals I squared R, where I is the current and R is the resistance. This means that even a small increase in current will increase the heat dramatically because the current is squared. In some cases, we use this heating as an advantage. For example, the filament inside a bulb glows because Joule heating makes it extremely hot. The same effect is used in electric irons, water heaters, and many other heating appliances. But in most situations, Joule heating is a problem. Almost every electrical and electronic device heats up because of this effect. If this heat is not removed properly using fans or cooling systems, the device can get damaged. But the more serious problem is the wastage of electrical energy. In almost all electrical and electronic equipment, a significant amount of electrical power is wasted because of Joule heating. The same thing happens in power distribution. Most of the transmission loss in power lines is due to Joule heating. Electricity generated in power plants has to travel through long cables for many kilometers before reaching our homes. Even though the cables are good conductors, a small amount of resistance is always present. Because of that, heat is produced continuously, and a huge amount of electricity is wasted. It is estimated that almost 30% of the generated electrical energy is lost daily in this way. To reduce this wastage, electricity is transmitted through high-voltage transmission lines. Before we discuss why high voltage reduces losses, we must first understand what electrical power is. We use electricity as a source of power. So before going further, we must understand what electrical power means and how it is calculated. To understand this, let us go back to our water tank example. Imagine that we want to run a machine using the water in the tank. For example, we want to rotate a turbine. If the tank is placed very high, the water has high pressure. With high pressure, a small amount of water flowing very fast through a nozzle is enough to rotate the turbine. But if the tank is not very high, the pressure is low, and the velocity of the water is also low. In that case, we need a large amount of water to rotate the turbine. Even the type of turbine used will be different. So to get a fixed amount of power from water, there are two possibilities: high pressure plus small amount of water, or low pressure plus large amount of water. Electricity works in exactly the same way. Electrical power is the product of voltage times current. If voltage is high, only a small current is needed. If voltage is low, a large current is needed to get the same power. Now imagine a city needs 100 megawatts of power. This electricity has to be brought from a faraway power station. In our homes, the voltage we use depends on the country we live in. Some countries use 110 volts, while many others use 230 volts. If we try to bring 100 megawatts of power at 220 volts, the current required will be almost 450,000 amperes. To carry such a huge current, we would need extremely thick and heavy cables. This makes the erection of transmission lines extremely expensive. And not only that, when such a large current flows, Joule heating becomes very high. A lot of power will be wasted as heat. But if we transmit the same 100 megawatt at 400 kilovolts, that is, 400,000 volts, the current required will be only about 250 amperes. In that case, a much thinner cable is enough. The Joule heating will be very small, and the transmission losses will reduce drastically. There is a massive difference between carrying 450,000 amperes and carrying just 250 amperes. That is why power transmission always uses very high voltages. But to do this, we have to first increase the transmission voltage at the power station and then reduce it to household level at the substation near our homes. The device that does this is called a transformer. Many people mistakenly think that if a transformer increases voltage, it also increases energy or power. But that is not correct. A transformer never increases or decreases total power. When it increases voltage, the current decreases. When it decreases voltage, the current increases. So the product, voltage times current, remains almost the same. In reality, even a transformer is not perfect. A small amount of energy is always lost due to Joule heating and magnetic losses inside it. So the power coming out is slightly less than the power going in. This difference is used to calculate the efficiency of a transformer. Now let us look at two important types of electricity, AC and DC. The first type is direct current, or DC. In DC, electricity flows only in one direction. The current from a battery is DC. Many people believe that DC is weak and cannot give a shock because the voltage from a normal battery is very low. But this is not true. There are many devices that use high voltage DC, and in those systems, an electric shock can be dangerous. The second type of electricity is alternating current, or AC. In AC, the direction of current keeps changing many times every second. For example, in many countries, including India and the UK, the direction of AC current changes 50 times in 1 second. So the supply is called 50 Hertz. In some other countries, like the United States, it changes 60 times per second. so their supply is 60 Hz. Electricity produced from batteries or solar panels is always DC, but when electricity is produced using a generator, it is much easier to generate AC. That is why almost all power stations generate AC. The biggest advantage of alternating current is that its voltage can be increased or decreased using a transformer. DC voltage cannot be changed using a transformer. So as we discussed earlier, if we want to transmit electricity over long distances at high voltage and then reduce it to a safe household voltage near the city, we have to use AC. For this reason, all countries use alternating current for power transmission and distribution. DC is needed mainly inside electronic devices, so every electronic device or its charger has a circuit that converts AC into DC before the device uses it. Now let us look at the speed of electricity. You may have heard people say that electricity travels at the speed of light. When we press a switch, the light turns on instantly. So naturally, we think electricity must be moving at light speed. But there is a small twist in this story. The actual electrons inside a wire move extremely slowly. Their average speed of motion is called drift velocity, and in a normal conductor, it is only about 0.2 millimeters per second. That means an electron travels just 1/5 of a millimeter in 1 second. So if electrons are this slow, why doesn't the bulb take many minutes to glow after flipping the switch? To understand this, think about our earlier water tank example. Imagine a long pipe that is already filled with water and there is a tap at one end. When you open the tap, the drop of water that enters now does not reach the other end immediately. But because the pipe is already full, the drop entering at one end pushes a drop out from the other end immediately. Similarly, even when a circuit is switched off, all the wires are already full of electrons. They are just not moving. The moment we switch it on, the first electron enters the wire at one end, and instantly another electron comes out at the other end into the bulb. In the bulb filament, electrons immediately start flowing out the other side of the wire, so current begins almost instantly. Not because the electrons travel fast, but because the electric field that pushes them travels nearly at the speed of light. When the first electron is pushed, its electric field pushes the next electron, and that one pushes the next, and so on. Since the electric field moves at the speed of light, this chain of pushing reaches the bulb almost instantly. That is why the light turns on the very moment you flip the switch, even though the electrons themselves are moving slower than a snail. I hope this video helped you understand at least a few important things about electricity. If you still have doubts or questions, feel free to ask them in the comments. I will try to explain those in another video. If you found this video interesting, do not forget to like it. And if you think your friends will enjoy this, please share it with them. Thank you.